Hi, Carly.
Thank you, and thanks everyone for coming. So yes, I am going to be telling you about locomotor adaptation. So really quickly, why do we care about locomotor adaptation? When someone has a stroke, they can have a limp that develops because of the lesion, and this disrupts their gait asymmetry. So you can imagine that we can quantify their gait asymmetry with a measure that we call step length asymmetry, where we compute step lengths as the distance between ankle markers during forward leg heel strike. And if we take the difference between two step lengths and normalize it by the sum, we get a unitless measure that is 0 if people are walking symmetrically and non-zero if people are not walking symmetrically. So what we can do then is we can have people walk on a split belt treadmill that disrupts the symmetry between their legs, and we can quantify how their symmetry changes due to this. So the split belt treadmill has 2 belts, as you can see. Each belt is independently controlled, so we can make one belt move faster than the other, and this is how we disrupt step length asymmetry. So what does this look like? Here you can see during pre-training is a child that has asymmetric gait, and so the leg that's farthest from us is not swinging as far forward, for example, and after walking split belt, when the belts are again moving the same speed, that you can see that the gait is visibly more symmetric. So the leg that's farthest from us is swinging farther forward. So there's this huge clinical potential for this sort of protocol, but there's also a lot of just basic research interest in terms of how locomotion is adapted. So that was the motivation behind this study. And so what I've been working on is I've been trying to collect as many split belt testing sessions as I can. So far, 5 institutions have contributed just over 690 samples. And so these are being put into a database that will be released. And what's in the database? So there's subject demographics. So you can imagine things like height and weight, but also information such as clinical diagnosis. So right now, about 7% of the population includes people who have either neurological or biomechanical diagnoses. It also includes information such as baseline step length asymmetry. So again, this is information about which leg moves faster. And you can imagine that, you know, this equation is defined based on what we're going to make people do during adaptation. So the step length asymmetry magnitude is a subject demographic, but the sign of their step length asymmetry is experimenter controlled, because the experimenter decides which leg they're going to be putting on the fast belt and which leg's going to be on the slow belt. And we're also including information about the training protocol that they receive. So you can imagine that during split belt walking, people walk this way and we look at the changes in their gait before and after training, but the training can be different. So you can imagine that maybe some people train on the split belt treadmill for a longer duration, and there's several other modifications to the split belt protocol that different laboratories use for different reasons. So again, the goal of this is we have this subject demographic information and we have the training protocol, but we want to be able to predict whether the gait training or the locomotor adaptation was successful. So what do I mean by that? So we want to see that people change their gait during post-training compared to what it was during pre-training. And we're going to be using, again, this measure of step length asymmetry to see specifically, does the step symmetry change? And so that's a continuous measure. So we actually need to binarize it for a classification problem. So we binarize it using a clinical threshold for what constitutes a significant change in gait symmetry. All right, so then what is the approach I use? I use a numerical approach. So I take several different classifiers and hyperparameterizations of the features that control the classifier. So for example, how many nodes do I allow, or how deep do I let my random forest get? And then I have my training sets and testing set, and I actually break it up into 4 random training and testing sets for my data. And this results in about 500 unique models that are each trained on 4 sets of my training and testing data. And I have these 4 sets of performance metrics from that. So what do I mean by performance metrics? I'm just going to show you one of the performance metrics that I use to give you an intuition. But in these kinds of studies, there's something called the receiver operator curve. So what's along the x-axis is the false positives over the total negatives, so the false positive rate. And then on the y-axis is the true positive rate, or how many true positives we identify, the total positives. And we can look at how a single classifier performs. And we might get a line that looks like this, but what we're truly interested in is the area under the curve. So we get this measure that I'm going to be abbreviating AUC, which corresponds to the area under the curve. But the idea being that if the area under the curve is closer to 1, it means the classifier is performing better. So what are we doing here? So we have these 4 different performance metrics for each model at different cuts of the data. So what am I looking for? How am I going to identify robust models? So one thing I'm going to be looking for is average performance. So I'm looking for a model that performs well on average. Here we can see that this yellow model is not performing well on average, so I wouldn't be very interested in investigating this model more. Looking at the orange model, we can see the average performance is better, but it's very variable across different sets of the data. So we want something that would have more stable performance. So actually looking to identify models that have stable performance across different subsets of the data, and the average is high. And so to give you an idea of what that might look like, here is the AUC data for all of my 500 models, and I'm highlighted the models that meet my criteria for the AUC performance metric, but also several other metrics as well. So I'm identifying a subset of the models as robust. And so I actually am still identifying quite a few models. So we have just over 260 models that I identify as robust. But now that I've identified these models that are performing well, what am I going to do with that? Well, I want to understand how they're performing well. How are they able to classify the protocols? So this is an example of how we can look at the importance of a single classifier. So this is one classifier. These are what's along the x-axis is all the features or all the predictors in my model. And what's along the y-axis is a measure of how important that feature was for the performance of that model. So you can see here that the duration and the baseline step length asymmetry are both very important features for this particular model. However, there are many models and they all perform, they can use different combinations of features to perform well. So here is a visualization of all of my robust models and how they were able to perform well, what features were important to them. And you can see that for some of them, the duration is important, and some of them that's not the case. So I'm just going to be pulling out a single model to make some points about this, but you should know it is variable how these models are performing. So to visualize how this model, like the actual predictions it makes, I'm going to be showing you a partial dependency plot. So what's going to be along the y-axis is going to give you information about the likelihood that a given session of split belt adaptation will be successful. So higher values mean that it's more likely to be successful, and lower values means it's less likely to be successful. Along the y-axis, I'm going to be showing you the baseline step length asymmetry values. And then along the rightmost y-axis, I'm going to be showing you information about the distribution of the data within the training set. So what you can see here is that when subjects have negative step length asymmetries, they seem to, on average, perform better. They are more likely to have a successful adaptation. Whereas if subjects have a negative step length asymmetry, they're less likely to perform well. Now, you might originally think that, oh, that's just because of the clinical data. And what I've shown you here is, so in the pale orange, that's the control data. So you can see we have a lot of control data, and we have some clinical data, but you can see that most of the clinical data actually is on the side where we would predict a higher probability of performing well. So this trend is not being driven by clinical data. It's being driven mostly by control data. So why is this interesting to us? Well, if you have a subject come in and during baseline walking, you notice that the leg that takes the longer step length is the leg that you would plan to put on the fast belt, you can change your protocol and decide to put that leg on the slow belt instead, and therefore reverse the sign of step length asymmetry. And this person is more likely then to have a successful gait training outcome. And I think this is important because a lot of times when we make decisions about which leg goes on the fast belt and the slow belt, every lab does it differently, and it's an important metric. So just to summarize, what did we actually find? So the classifiers are working decently well. We have some reasonably good performance metrics. The way that these classifiers are performing well is they're using a combination of both subject demographics and protocol details. So specifically, the baseline step length asymmetry is a feature that's being used often and something that we don't consider when we're working with control data, and the results from this study indicate that we should. We also see that the duration is occasionally a very important parameter, and this specifically means like if you train more, you're more likely to have a successful outcome, which I think is quite intuitive. So future work, the data set needs to grow. We need more kinds of data. We need more older adults, more clinical populations. So I'm still collecting data. So if you have split belt data that you would love to share, please do. Also interested in better understanding if maybe the model makes different predictions for different populations, and trying to also do a population-based cross-validation. So if we train just on young subjects, do we see that the model that we generate also works well for older adults, for example? I want to thank all my collaborators and funders. So Emcee and Rayed are supervising this project. They're from Pitt and CMU. We've had several institutions contribute data, and we've had a lot of monetary and computational support from different institutions. But thank you for your time. I'd be happy to take any questions.
Awesome, Carly. Thank you so much. We have a question for Scott that I'm going to circle back to. I'm going to abuse my power as MC and ask my question. In the meantime, audience, please fill your chat. I guess, so one of the things I was wondering, and I have no knowledge of this area, so excuse me if it's a bit stupid. Do people, when you see these positive results after the split belt training, how long do those positive results last for? Like once the system is back online, they're good to go, or does this need continued maintenance?
Yeah, so if you adapt a young healthy person for 10 minutes, they're going to have after effects that decay and are gone in about 5 minutes. And we look my laboratory and a lot of this data is single session data. However, there's other work from Johns Hopkins and other institutions that have done like true training interventions where they do repeated exposures and they see long-term effects, effects that last a long time, but also are of a greater magnitude than we would expect from a single session. So just like anything, you would have to do it repeatedly to gain clinical benefit from the intervention.
Awesome. And do you think of like that, if you were trying to find like features that contribute to longer term results, like that the model would have to weight these differently?
So that's a really interesting question. I think right now it's very speculative. So we, think if we find something that works well for a single session, that it might help long term. But a lot of those things that we, have observed work are helpful on a single session. We're not really sure if it actually propagates long term. So it's possible that some of the things that benefit performance in the short term don't benefit in the long term, and that mostly has not been experimentally tested.
Right. So we have one question from the audience. What of your metrics is the most important for your real-time application?
For my real-time application, if someone wanted to clarify what they meant by real-time, I'll answer the question based on what I think that means. So right now, I think that it's very difficult to understand what complex interactions are happening, and that affects, me as an experimenter. So I look at my data and I have one young subject that does something weird during adaptation. And I don't know why. And I think some of these things could maybe, post hoc help me understand my data better, but also help me understand other researchers' data. So if someone did a very similar experiment to me and they have a different result, it could be that they chose, a silly example, but maybe they adapted their subjects longer, and that's why we have different results. Or maybe they chose to put a different leg on the fast belt, and that could explain our results. So right now, it's really helping us interpret data we already have. But long term, I do hope that it could be used to find an optimal protocol for clinical applications.
Right, yeah. Hi Carly, great talk and project. Curious about the catch parameters. First, to make sure I understand correctly, does that mean the protocol included a catch trial? And second, why do you think that has such a high weight on average?
Yeah, so this is it is a binary. Was there a catch? Were these after effects measured in a catch, or were they not measured in a catch? And so the reason that this ends up being so important is if there is a catch, it could indicate. So if there's a catch, oftentimes we're measuring something else in a longer trial later on. So there's adaptation, catch, readaptation, and then something else. And it's usually some sort of a generalization protocol, but it could be, the ordering really depends on the study. So that particular metric, I believe, is so important because it indicates whether that was the first time the after effects were measured. And we know from, many people's work that the first time that you measure the effect of the training, you're going to get the largest magnitude, and that kind of decays the more that people practice switching in between the training context and a non-training context. So I think that, I hope that clarifies, but that's my understanding of why that's so important.
Awesome, thanks. So we are not going to get kicked out of this room.